Assalamualaikum warahmatullahi wabarakatuh. Okay, let's go through for the case A, the solution for case A, heat equation. Okay, this is for heat equation. Okay, for case A. Okay, let's say we want to solve U dst. This is the equation for the heat equation, standard equation, subject to the U0t equal to 0 and ULt equal to 0 for t greater than or equal to 0, and U as not equal to Fx. This is the initial temperature. Okay, for x between 0 to L. Okay, this the solution will be, the first thing we need to apply the separation of variables. Here, separate the variables. The equation that we have is ut, that means x of x t prime t, and here k u as x, which means k x double prime x t of t. Okay, and we separate the variables, and here we have x double prime x over x of x equal to t prime t over k t of t equal to p, which is a constant. For me, you can actually directly write it as negative lambda squared. Okay, because as you can see here, to satisfy with the conditions that when u approaches 0, t approaches infinity for all x. Okay, that's why we need to choose p equal to negative lambda squared. Okay, there's a reason behind the choice. That means to satisfy the conditions that the temperature should be approaching 0 when t approaches infinity. Okay, that's why here we choose p equal to negative lambda squared, and hence the equation here will be x double prime x plus lambda squared x of x equal to 0, because we bring the denominator to the right. Okay, and then we equal to 0. Next is t prime t here equal to k t prime t plus k lambda squared t of t equal to 0. Since this one is positive, when we bring it to the left, it should be positive then. Okay, and remember one thing, the constant should be with t. Okay, the constant cannot be with x. Okay, and then which implies here the auxiliary or characteristic equation where we apply m. Okay, for double prime, m squared is for double prime, m is for prime, and m power of 0, which is 1, equal to 1 is not differentiate. For example, s of x or t of t. For x of x, we have m squared plus lambda squared equal to 0 here, because s double prime x, right? So this one should be m squared plus lambda squared then equal to 0. And for t of t, we have m plus k lambda squared equal to 0. Okay, when we solve for x, we have m equal to plus minus lambda I. Therefore, x of x is equal to a1 cos lambda x plus a2 sin lambda x. Okay, and for t of t, we have this first order equation, and therefore this one should be in box 2 actually. T of t is equal to b exponent negative k lambda squared t. Okay, just write any constant. Actually, if you want to write here a3 is also okay, but it's just that we want to differentiate the constant for x and t. That's why we represent the constants in terms of a, and for t of t, we represent the constant in terms of b. And therefore, the temperature of the rod is U as t, which is x of x times t of t, given by a1 here cos lambda x plus a2 sin lambda x multiply with this t, b exponent negative k lambda squared t. Okay, the boundary conditions here are used in order to find the values of the constants a1, a2, and lambda. Okay, and given that the first condition u0t equal to 0 and the second condition is ult equal to 0 for t greater than or equal to 0. So the first one, u0t means x0, because this is actually the part for x, right? So x0 t of t equal to 0, which implies that x0 is equal to 0 for some arbitrary t of t. Okay, we substitute into the solution x of x. We have x0. This is your x. Okay, s of x, a1 cos lambda x plus a2 sin lambda x. Okay, when we substitute x equal to 0, we actually have this one first. x0 equal to a1 cos 0 plus a2 sin 0. Okay, sin 0 equal to 0. So a1 is equal, cos 0 equal to 1. So that's why x not equal to a1 here. Since x not equal to 0, x0 equal to 0, so this one is a1 equal to 0 then. Okay, so next, therefore the solution s of x can be rewritten as s of x a2 sin lambda x only. Okay, because a1 is 0. Okay, next is the second boundary condition, which is, I should highlight this one, ULT equal to 0, means s of L, t of t equal to 0, which implies that s of L equal to 0. The first one is s0 equal to 0. So the next one is s of L equal to 0 for some arbitrary t. Okay, here. So we substitute this one into the solution s of x. Okay, we have s of x is equal to, earlier, s of x is equal to a2 sin lambda x, right? So we substitute. We have the next one is x of L should be equal to 0, the second condition. So x of L is equal to a2 sin lambda L equal to 0. Okay, if a2 equal to 0, then the solution is trivial. That means there will be no solution then. A1 is equal to 0. And if a2 equal to 0, there will be no solution. That's why it must be sin lambda L here should be equal to 0. Okay, which implies that lambda is equal to n pi over L. The reason behind it, remember what we learned in Fourier series, sin n pi equal to 0. So right now we have sin lambda L equal to sin n pi. So lambda L is equal to n pi. Lambda is equal to n pi over L. Okay, for n equal to 1, 2, 3 until infinity. Compulsory for you to write this. Okay, and note that n equal to 0 is not included, because if n equal to 0, then lambda equal to 0. Okay, because when n equal to 0, that means here lambda will be equal to 0, right? So sin lambda L cannot be equal to 0. That's why it starts at 1, from 1. Okay, and then therefore for n equal to 1 to until infinity, the solution for x of x and t of t will become s n. You need to write n because there is a repetitive of n here. Okay, so x and x equal to an sin n pi x over L, and t and t n of t is equal to b of n exponent negative k lambda squared, right? So n pi over L squared t. Okay, and the solution for u as t will become like this, because x of n times t of n. Okay, and can be rewritten as this, because we multiply an and bn. So capital letter Cn is equal to an times bn. It's just that we want to simplify the equation. After that, we apply the superposition principle. This is the theorem. Okay, if u1 until un are solution of a linear homogeneous PDE, then the linear combination for u is equal to C1 u1 until plus until Cn un, where C1 until Cn are constants, which is also a solution. Okay, and next, by applying the superposition principle here, we will have this UST as such. Okay, from this term. So that means we can just write it as, we don't have to write it like this anymore. That means you don't have to add for n equal to 1, 2 until infinite. Okay, dot, dot, dot. You can just write it in terms of summation. That's what it means. Okay, the superposition principle means anything that you need to write at the end for n equal to 1, 2, 3 until infinite, you can change it into summation. Okay, summation n start from 1 here. Okay, and from 1 until infinity. Why infinity? Because dot, dot, dot. Okay, until infinity. Okay, c of n exponent negative k lambda squared, so n pi over L squared t sin n pi xl. Okay, always write sin the trigonometric function at the back. Okay, because it's properly written if it's at the back. Okay, with the initial condition u as not equal to fx, And therefore, when u is not equal to fx, that means we substitute t equal to 0, right? So here, t is equal to 0. When t equal to 0, okay, exponent negative k n pi over L squared times 0, which means it will be exponent 0. Exponent 0 is equal to 1. That's why we are left with only this in the equation. Okay, summation n from 1 to infinity, Cn sin n pi x over L, which, if you look closely, this is actually a Fourier sine series. Okay, and the constant C of n, okay, it's just like how we calculate for B of n in Fourier series chapter. So right now, it will be C of n then. Why? Because this is the coefficient. Okay, so C of n equal to 2 over L integrate 0 to L fx sin n pi x over L with respect to x. Okay, that's it for the intro, and we will look at the example for case A and later on for case B in the other two videos. Thank you. Assalamualaikum.